Oh, well, that's okay. I think everyone's actually here today, so that's good, you know, so nobody's entirely missing this. All right, and we're going to take a little look at what happens, because if we have water which has positive and negative ends, it can interact with a positive and negative sodium ions. Yes? So we're going to unmute this. Hello. There we go. Okay, and we are going to go to here, and we're going to watch, there's 3 videos about the dissolving of salt. Each of them are very short. I just felt like I couldn't decide which one was best, so I picked all 3 because they are really short. We're going to watch all 3, but they're like super short. They're like, I don't know, a minute, 2 minutes. Oh boy, speedy today. Video unavailable? What? Oh, that's okay. I have 2 others. Okay, let's go to the next one. Okay. Hooray. Okay, this one seems to work. I know, right? Huge and long, yeah.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay, so do you remember what charge was the hydrogen on the water? Slightly what? Positive. Okay, and you can kind of remember that because an H, if you don't draw it very well, it's kind of like 2 positives, yes? See? Hydrogen, it's a little bit positive. Okay, so that might help you remember that the hydrogen is a little bit positive, the oxygen then would be a little bit negative. And look at where the hydrogens are pointing around that sodium ion. The hydrogens are pointing towards the sodium because those hydrogens are, those positive hydrogens are attracted to the negative sodium, the negative chloride. The negative chloride is attracted to the positive hydrogens. Okay, over here, you can see the red oxygen is attracted to the positive sodium, and the positive sodium is attracted to the red oxygen. I want you to watch it one more time. I'm actually going to turn off the sound so you can just focus on watching, and I'll slow it down just a little bit. Yeah, that's the entire video, right? So what we're going to do is we're going to slow it down, and you're going to watch the negative ends of the water go in and grab the positive ions, and you're going to watch the positive ends go in and grab the negative ions. It may take a while because we're on half speed. Here they go. Oh, look at those little negatives pulling away the positive, and the little positives pulling away the negative. Positives pull away negative. Negatives pull away the positive. Okay? is good? Yeesh. Onions are larger than cats. Sure. I like that, okay? And we could actually watch the other one now. Let's go see. Oh, and we'll turn our sound back on. It's 1 minute and 35 seconds. Whoa. I don't know why the quality is so bad. Polar charges on the water molecule. Les charges de la molécule de chlorure de sodium. I apologize to anyone who actually speaks French. Woo! Wow. Why is it only what? And eventually, and this is what was not shown in the other one, can you see what's happening? Everyone is pulled apart, and what kind of a mixture do we end up with? A solution, otherwise known as a homogeneous mixture, yes. Okay, excellent. All right. So here's just a little picture at the bottom of the page showing what it looks like to start with, you know, little still shots. And you can see when it's starting to dissolve, there are some of the particles which have been taken away and surrounded by the water molecules, and eventually the entire thing is dissolved. We haven't shown all the other water molecules in between, otherwise it gets too cluttered, and it's hard to see the orientation of the ones around the ions, okay? We are going to learn a new symbol, if we've not already learned it. I don't think we have. Have we? The lowercase delta? Oh, right. That symbol like there, it looks like a D, but it also looks like an S. This is a lowercase delta. And it means partially or slightly. So you might be asked to draw a sodium ion and to show the correct orientation of the water molecules around it. Okay? Or you might be asked to draw a chloride ion with the correct orientation of water molecules around it. Which way do the water molecules orient themselves? Which way do they arrange themselves around the positive ion? They put it so the negative is pointing towards the positive. Mickey Mouse heads are all negative, and it's all those Mickey Mouse heads pointing towards sodium. Over here, it's all the ears, all the positive ears point themselves towards the negative chloride. Yes? Oh, there's not. It's because that's easy to draw, right? I mean, honestly, it's a three-dimensional thing, so it's actually a sphere around them. It would like surround them to whatever extent is possible. How do you determine what? If a molecule is a polar molecule, you have to look at its shape and you have to look at its electronegativity, which is just a big word for saying how well atoms pull on electrons within a bond. There are charts with tables like of electronegativities that says these things are more electronegative, these things are less electronegative. No, you wouldn't know it immediately. Now, if you're interested in the overall trend, the most electronegative are at the top right of the periodic table, and the least electronegative are at the bottom left. And hydrogen kind of does its own weird little thing. It sort of is, this is your periodic table. And electronegative just means able to pull on the ability to pull on electrons in a bond. We will get to this later, but for now we won't worry about it too much. Okay, you can just believe me that oxygen is more electronegative, and so it pulls on those electrons more, and so you end up with a slightly negative oxygen. Okay. Now you can imagine if you had a molecule, if water were instead shaped like this, rather than being bent like Mickey Mouse, I would have a slightly negative middle, and then each of the ends would be slightly positive, which would end up in a non-polar molecule because you don't have a positive end and a negative end, you just have two ends that are negative overall. Okay, so that's way beyond what we're doing at this point. That's a totally other unit, but that's the general idea. Okay? You don't need to, if I ask you to draw that, you don't need to draw 6. You could draw like 4, but you could draw 5, whatever you can make fit around the ion, that would be totally fine. Okay. So that's what's happening when we are dissolving. Shall we take a look at somewhat of the reverse process? The undissolving? Ooh, what is undissolving? So we are learning a couple new vocabulary words here. So this is page 110, 110. Solubility. Solubility is the maximum amount of solute. Do you remember what solute is? Tell your partner, what is the solute? The stuff that gets dissolved, yeah. So it is the maximum amount of solute that will dissolve in a given volume of solution. Can you think of a unit we could use for that? Try and brainstorm a unit for solubility. We want the amount of solute in a given volume of solution. Chat with your partner, see if you can come up with something. So that's for a pure substance. This is slightly different, but yes, it's the same. So what have we got? What would go on the bottom? Some sort of volume. So you could have liters, or you could have milliliters. You could have centimeters cubed. Okay, generally when we're talking about volumes of liquid, we don't use centimeters cubed. That's used more for solids. So we will generally use liters or milliliters. Those are like liquid volumes. Now, what could we use for the amount of solute? We could use grams. Do you remember another unit that measures amount of matter? The mole. So we could have moles per milliliter or moles per liter or grams per milliliter or anything like that, okay? Holy moly. Oh, yesterday was mole day. 10/23. Yeah, it's like a big thing in the States. They do all kinds of stuff, but we're never at the mole by October, so we're like, oh well. Oh, it's not. It's going to be different for every substance because it's a number of particles. So it's going to depend on the size of the particles, how closely they're packed. It's going to depend if it's a gas. A mole of gas takes up way more space than a mole of a solid of the same substance. We actually usually convert it to in and out of grams because grams is something we can measure. We can't sit there and count out particles. I don't know if you remember from the quiz we wrote, 1 mole of molecules, yeah, is 6.02 times 10 to the 23 molecules, and that's like a huge irritating number. You can imagine sitting there counting particles, 1, 2, 27, 28, 135, 4,362, 4,363, and you're nowhere near even close, right? Like you just can't. But the nice thing to know is that 1 mole of carbon atoms, for example, has a mass of 12 grams. And that's useful because then you can weigh out 12 grams of carbon and you know you have that many molecules or atoms. Okay? That's what a mole is really used for. It's really to allow us to weigh out atoms or molecules and know how many particles there are by doing some conversions. Okay? Because nobody wants to count atoms even if you could, which you can't because they're too small. Okay, so we were talking about solubility, the ability of something to dissolve. It can be measured in grams per liter or moles per liter. And remember, it is the maximum amount of solute. What does it mean to be the maximum? You cannot put any more in. What kind of a solution do you have if you can't put any more in? It's called a saturated solution. It is a solution that contains the maximum amount of dissolved solute. Okay? So let's say you wanted to find the solubility. Like I gave you some salt, and I said, find the solubility of sodium chloride for me, please. So you want to find the maximum amount of solute that will dissolve in a given volume of solution. What could you do to find the solubility, the maximum amount of salt that can dissolve in a given volume of solution? What would you have to do first? You would have to find some mass. You would have to you got your water here, yes? What are you going to do with the salt? You got salt. You got a dish of salt. You got your water. What are you doing with the salt? You're putting the salt in the water and you stir it. Oh, it's all gone. What do you do now? Drink it? Ugh. Make yourself sick. Am I going to be able to find out the solubility of the salt from this salt water that's had one scoop of salt put in it, stirred around, it is now all dissolved? Is that going to tell me the maximum amount of solute in here? So let's imagine, here we go, here's our little picture. Because I don't know how good you guys are at doing this in your heads. Whenever I talk about things like this, in my head, there's literally like a little person, like I'm like, oh, and I'm watching the particles dissolve, right? So we take our salt, and then we stir it, yes? And then we end up with that. And we're like, oh, okay. Have I dissolved the maximum amount? How could I have dissolved? How could I know I'm at the maximum amount? It all dissolved. Wouldn't that be kind of a fluke if I added exactly the amount that was needed to make it full? What should I do now to make sure that it's full of solute? Add more. Okay? Stir. Uh-oh. It's still clear. What should I do? Maybe add more salt. And stir. What will I see eventually? Eventually, I'll see stuff that does not dissolve, right? Is this ringing bells? Yeah. So what could we do with this? Because now I want to know how much was dissolved in there. What was that maximum amount that dissolved? I could filter it. Okay, so you're filtering out the undissolved salt. What would you do now? We now have a piece of filter paper. And it's got undissolved salt on it. And we have also solution containing the maximum amount of salt. You could go 2 routes on this. You could do something with this. You could do something with this. Chat with your partner. What would you do? So what are the 2 ways we could go? What's one way we could go? What's one way we could go? You guys are too shy. I know it's hard to speak up in class because you're like, oh my God, I don't want to be wrong. Oh my God, I don't like talking in front of people. Can you imagine how bad I'd be at my job if I was worried that I'd get it wrong? Because do I get it wrong on a relatively frequent basis? You guys have seen my answer keys. I get it wrong on a relatively frequent basis. Yes. You'll give your way. Okay, what's your way? That's okay. Yeah, yeah. So here's our idea. We take the mass of the salt that we added, that we dumped in, and we subtract the mass of the salt on the filter paper, which would require us to know the mass of the filter paper, yes? The only thing I'm going to change from what you did, you said take the volume of water that we put it in initially. This is the solubility is the amount of solute per milliliter of solution. Solution's volume will be higher than the amount of the water because the solute takes up space. Huh? No, we want the volume of the solution after. Yeah. So what we want is we want the volume of the solution collected after filtration. Yeah? Because otherwise you're doing mass of solute over volume of solvent. Yes. Okay, now what was the other way? We had another way back here somewhere. Stuart, your way's faster. What's your way? Yep. Yep. Okay. Uh-huh. Okay, I got lost. Okay, but I could not follow it. But it sounds the same as your method. It is a bit different, but they are all involving the mass of salt undissolved. There's a way of doing it without using the residue at all. The residue is the solid left on the filter paper. There is a way to do this using only the filtrate. Ooh, what? You could just boil it. You could measure out a certain volume of the filtrate, the liquid. Of the filtered, saturated solution. And then once you have done that, you can evaporate it to dryness and take the mass of the salt that it remains. You can find the mass of a beaker. You could find mass of, and you could boil to remove the liquid. And there we go. Okay, that was exhausting. However, all the steps are right here for you. Look at this. Oh my gosh. They are right here. Okay, so you can follow through there. I don't have the other method written out, but that's okay. Would we like to see what, oh, you know what, we're out of time, aren't we? We have 1 minute. Why don't you guys watch the video? We have a 30-second video. Okay, here we go. Homework, read pages 113 to 115.
So here's the dish of water. And if we look very closely, the water molecules are evaporating. And as they evaporate, the concentration of the sodium and chloride ions increases, and the charges bring them closer together, and the attractions hold them together, and they recrystallize as salt. And that's why students see those tiny salt crystals in their dish after the evaporation takes place.
No, not page 118.
Possible to come during lunchtime because I have skating in the morning, so I won't be able to make it to class.
Yes.
I'll drop by tomorrow lunch.
I always forget to stay at lunch, though. That's the only issue.
Alright, I'll try to make it over quickly then.
Okay. Yeah, if you're here like right at the beginning of lunch, I will remember.
Alright, got it.
I'll write your homework on Teams because I don't think I got it right.
Alright.
Okay, see ya. Yes. It's just normal flex on Friday. No problem. Oh. Sorry. Thank you. Hi, I'm all right. How are you?
This week?
I don't think so. No. Next week. Yeah. Yeah, because we are finishing off the unit. Yeah, it'll be next week. Okay. Where are we? 11 enriched. Boom. Hi.
So you know, so far we've been like trying to figure out if the changes are like endothermic or exothermic.
Yes.
Can these be physical changes?
Yes.
Because like so like ice melting would be like endothermic. 'Cause
Yes.
It's like absorbing heat, right?
Yep.
Oh, okay.
Yeah.
I was looking at that all that and then I was
Yeah.
it can be physical too.
Yeah.
Okay. Thank you.
Yeah. Yeah.
Oh, also, like fire releases heat, right?
Yes.
So technically the fire itself gets colder.
Yeah.
Like how does that work?
Well, I mean, it's not that the fire is getting colder, it's just that the potential energy in its bonds is being released to the surroundings. Fire is not getting colder, the surroundings are getting hotter.
So like with the wood, if we're like burning wood, would that be part of the system?
That's part of the system.
Yeah.
Yeah.
So the wood's also like.
Sorry?
Is the wood also losing energy?
Folks, I have someone standing a foot away from me and I cannot hear her question.
No, would the wood also be like absorbing or releasing heat?
The whole because it's part of the system, yes, it's releasing heat. Yeah. Yeah. Hi.
I'm not gonna be able to be here on Wednesday.
Okay.
Because housing competition.
Okay.
But I don't know what are we doing. We're doing a stick trader, right?
Yeah, we're gonna be working on that. Yeah.
So maybe I can catch up on you.
Yeah, probably. Yeah. Yeah.
Well,
No
thanks.
problem.